Welcome to a brief lesson on finding the location of lines of constructive and destructive interference in two-dimensional space. In this example, you can imagine two sources that are in phase, giving off, let's say, a sound or something like that, that are separated laterally from one another. And as you separate the two sources, you should know from previous study that you get some sort of a pattern of constructive and destructive interference that looks a little something like this. We'd like to be able to come up with a mathematical equation to calculate how to find the lines of constructive and destructive interference. And this is how we'll do it. We'd like the reference line that we draw between the two sources, a line that connects the two sources. We could call that the baseline. We'll just use that for reference. Draw another line perpendicular to that that's through the center between the two sources. And what we would notice that our first line of constructive interference occurs along that center line. If we wanted to explain why this occurs, we would say something like this. If you notice there's some location in space way out, far away from the sources, would have waves coming from one of the sources. And in this case, what we show is the red dots, let's say, would be the peaks, and the spaces in between would be the troughs for that wave. We would draw the wave from the second source, and you'd notice at our location out there that the waves line up. In other words, peaks overlay peaks and troughs overlay troughs, which is our definition for constructive interference. And it turns out any place along that center line, you'll find that this exact same alignment occurs, and you'll get constructive interference. Now you'll notice also that there are other locations where you can get constructive interference. For example, if I were to, you can see this line right here is another line of constructive interference. I could choose a location out in space away from the sources, and I could do the same thing, is draw the wave from one of the sources, draw the wave from the second source, and you would notice at this location in space, again the waves line up. In other words, peaks overlay peaks, troughs overlay troughs for constructive interference. Now you might ask yourself, why does this happen when clearly from the marked location, the distance to each of the sources is not the same? Well, in this example right here, if we were to draw in a small reference line, something like this, you'd notice that if you counted to the right of the reference line out to our location in space that we've marked, you'd count exactly the same number of dots. But notice that the distance between our location in space and the lower source is exactly one dot further away. In other words, it's one wavelength shifted from the other one. You should know from your studies, if you take two waves that have exactly the same shape, shift them by one wavelength, then you'll get the two waves lining up again and have constructive interference. That should be a review just of your kind of conceptual ideas associated with this picture of two-dimensional interference. But what we'd like to do is develop a mathematical equation to find out essentially what we'd like to know is this. We'd like to know this angle here between the center line and our first line for constructive interference. And let's go ahead and do that derivation. It looks a little something like this. What we'll do is I'll go ahead and get rid of the wave patterns to simplify our picture a little bit. And then what we're going to want to do is zoom in on just this portion of the diagram. So you can kind of see the two sources there and the rays going away from the source. When we zoom in, we get a little something like this. A little blurry, but you can kind of see the waves coming off the first source going in that direction, the waves going off the lower source in this direction. And it turns out the key for our mathematical derivation here is going to lie in this triangle right here. So let's just label some of the sides of that triangle if we can. First one we'll label as this one. It's pretty easy. We use this kind of italicized D to indicate the distance between the sources. You'll notice that's the hypotenuse of that triangle. Next, what we'll do is we'll label this side over here delta D, which is our path length difference. That's the technical name for the fact that you'll notice from our source that's way off to the right, we said that it is one wavelength further away from the lower source. And you can kind of see that one dot extra that the lower wave has to travel to get to our distant location. And so that is the path length difference, or the difference in the paths of the two waves. And we'll label that delta D. Finally, the third thing we can label in this triangle is this angle right here, theta. Now this is a little bit more difficult to see. You may want to go back to the diagram and just do a little easy geometry to verify that this is the case. But it turns out that the angle that we're interested in, which on the big diagram, if you remember, is this angle right here, theta. It's the angle between the center line and our first line of constructive interference. That angle, it turns out those two angles are exactly the same. And again, you can use a little, test it out with a little bit of geometry, and you'll see that those two angles are the same. Now looking at our triangle, you can kind of guess that we're going to do a little bit of trig. We have an angle, we have an opposite side, and we have a hypotenuse. So it would make sense to use the, I should mention one last thing here, is that this is not totally obvious, but you'll notice that those two waves that are going away from the source are almost parallel. I say almost because as long as your sources are very distant from the points you're measuring, those two lines will be pretty close to parallel, which allows you to assume that this is a right triangle. Okay, so as soon as you know it's a right triangle, you can use trig. And in this case right here, we can use the sine function, and the sine of that angle will be the opposite side, which is our delta D, or path length difference, divided by little d, which is the distance between the two sources. And then this is the equation now that we've developed to be able to find out the location of any lines of constructive or destructive interference. Here's how it works back on our big picture. Looks a little something like this. So in this case right here, I would like to know, let's say, the angle between this angle right here, between the center line and our first, this isn't writing very well, sorry, between this angle right here, between the center line and our first line for constructive interference. We could write the equation like this. The sine of that angle is equal to the path length difference for any point along that line between the two sources. And we said before that for this first location, these two waves have to be shifted a path length difference of one wavelength. So that goes in the place of path length difference, divided by the distance between the 2 points. And now you can solve for that angle and find out what the location for that line of constructive interference. Similarly, you have another line of constructive interference at this location. We'll set this up the same way. The sine of that angle between the center line and all the way over to that location there is going to be the path length difference for that line of constructive interference, which will be shifted 2 wavelengths. And we divide that by the distance between the 2 points. And you can see how this equation can give you any number of constructive interference lines, the location for them, using the equation. We're not done quite yet, though, because it turns out this works just as well for lines of destructive interference. In this case, this line of destructive interference is a certain angle away from our center line. We can find that by using the same equation, the sine of the angle. And we know you should know conceptually and from other study, that whereas you get constructive interference if you shift the 2 waves by a full wavelength, you get destructive interference if you shift them by half wavelengths. And so in this case right here, if the first one is located when they've shifted a half of a wavelength, path length difference, divided by the distance between the 2 sources. And I can find this line of destructive interference. You probably know where I'm going with this. The sine of that angle between the center line and that destructive line is going to be 1.5 wavelengths divided by the distance between the 2 sources. And that's the mathematical way you can find the locations of constructive and destructive interference for 2D interference. Thanks a lot for joining me.